Hello everyone. Today we will learn the last part of the hypothesis testing, which is log likelihood ratio test. Chapter 10.11 is about likelihood ratio test, and if you learn about this, you will see that this is quite reasonable to derive. Okay, suppose that random sample is selected from a distribution and likelihood function L uh, is function of k parameters from theta 1 to theta k, and let large theta as theta 1 to theta k. Okay, and here in the likelihood, because the y1 and 2y and they are given, so the likelihood L is function of theta 1 to theta k. Okay, and suppose H0, the null hypothesis, lie in particular set of values of this, and the alternative hypothesis lie in another set of values. So the particular set of values, what it implies is that, let's say this is one set of parameter set, like theta 1 to theta k, and let's just say theta 1 to theta k is like 1, 1, if everything is 1, and this would be the particular set of parameters, and this one may be particular set of the null hypothesis, like this. If this set of parameters are inside of the null hypothesis, then we can write the null hypothesis as like this, and there are also alternative hypothesis, which is this one, and the union of the null hypothesis space and alternative hypothesis is the full space of the parameter. And let me give you an example so that you can understand better. If we sample from exponential distribution and with mean lambda, and let our test as H0 is lambda 0, and versus the alternative hypothesis is lambda is not equal to lambda 0. Then the null hypothesis, the null case, this is the set of values for null hypothesis. And what about a set of values for alternative hypothesis? It is all the lambda except lambda 0. So from the set of the lambda, which is greater than 0, there is a point lambda 0 here, and for this one is only this point. This point is inside of this lambda 0 point is inside of the omega 0, and all the other points lie in alternative hypothesis space. That's what this means, and from here omega 0 union omega a, this is full space, which is lambda is greater than 0. Okay. So generally, we can write our hypothesis, null hypothesis, and alternative hypothesis this way. The set of parameters are inside of the set of the this is set of parameters, and this is particular set inside of the null hypothesis space, and this is for alternative hypothesis. And let's define the likelihood, the maximum value of likelihood as this. So given this set, given this space, probably there's a theta that maximizes the likelihood. So likelihood is function of theta, likelihood is function of theta, and inside of the null hypothesis space, there should be the set of theta values that maximize that likelihood. And let's define that as likelihood of omega 0 hat. This is the maximum likelihood inside of the null space, and let this value as the maximum likelihood in alternative hypothesis space. So in this case, the theta live in the alternative hypothesis space, and we take the maximum value of likelihood in that space, and that's the L omega A hat. Okay, and in what situation we would prefer the alternative hypothesis space? So if alternative hypothesis is true, then probably this value, the L omega alternative hat, this value should be larger than null likelihood. So this implies that the best explanation for the observed data can be found inside of the alternative space. Okay, so this is how we can make the likelihood ratio test. So we compare the likelihood ratio between the likelihood of null space and likelihood of the total space, and we check whether this lambda is small enough. If the null hypothesis, if the alternative hypothesis is true, this part should be larger than this null likelihood, and so this one have smaller value. So smaller value of lambda is the evidence of the alternative hypothesis. So rejection region is determined by lambda is less than k. So this is the likelihood test, likelihood ratio test. Let's move on to example 10.24. Suppose that y1 to yn constitute a random sample from a normal distribution with unknown mean mu and unknown variance sigma square. We want to test the null, null is mu equals mu 0 versus the alternative hypothesis is mu is greater than mu 0. Find the approximate likelihood ratio test. Okay, so y1 to yn follows normal distribution with mean mu and variance sigma square. And here hypothesis is here, and using likelihood ratio test, lambda is the likelihood of omega 0 hat and the likelihood of omega hat. And this is less than k, and this is our rejection region of the likelihood ratio test. And so we want to calculate these, the likelihood. So the likelihood L theta L theta likelihood function for normal distribution can be written as like this: 2 pi minus 2 over n, and sigma square minus n over 2, and expected value of minus 1 over 2 sigma square, sum of I equals 1 to n yi minus mu sigma square. Okay, so this is the likelihood ratio, and how can we get L theta 0 hat? Here the theta 0 the omega 0, the space of this is mu and sigma square, where mu equals mu 0 and sigma square is greater than 0. This is space of the omega 0. And what about the omega, the whole space? And this is mu and sigma square, where mu is greater than or equal to mu 0, because the alternative hypothesis, the space is mu is greater than mu 0, and so omega alternative, the space have mu is greater than mu 0, and actually the whole space, this is omega 0 union omega a, so this is mu is greater than mu 0 and sigma 0 is greater than 0. Okay, and now the problem becomes finding MLE and put it inside of the likelihood, and so let's calculate the likelihood from here. So omega 0 hat, this is so let's calculate mu 0 hat and omega 0 hat, which is MLE of the null hypothesis case. And since we have one mu 0, so mu 0 hat is mu 0, and actually from the previous example, from example 9.15, we already calculated our sigma square estimate is 1 over n sum of yi minus mu 0 hat square. So I will, you can refer this example 9.15 to calculate the sigma square 0 hat, and so this is this one, and mu 0, MLE of mu 0 hat is mu 0. So let's just put it inside of this L. Okay, so L omega 0 hat is, we are putting these one to here, and so this one becomes 2 pi minus n over 2, and sigma 0 hat minus n over 2 times e to the minus 1 over 2 sigma 0 square hat, and here is sum of I equals 1 to n yi minus mu 0 hat squared. Okay, and if we divide n here and multiply n here, then this one is actually sigma 0 square hat. So these two guys can be cancelled, and so this part becomes e to the minus n over 2. Okay, so this one becomes 2 pi minus n over 2 and sigma 0 square minus n over 2 and e to the minus n over 2. Okay. Now let's move on to find L omega hat, which is to calculate this number, you need to calculate MLE under this space. And again, for the sigma square hat, using with the similar proof of the example 9.15, you can get your MLE estimator as this one over n sum of yi minus mu hat square. This should be MLE for sigma square hat. And what about mu? And the range of mu in omega space is this thing. And let's calculate the MLE for mu. And let's firstly take log of L theta, log of L mu. This is minus n over 2 log 2 pi minus n over 2 log sigma square and minus 1 over 2 sigma square sum of yi minus mu squared. Okay, and let's differentiate with respect to mu. And this is these are constant, and minus 1 over 2 sigma square and 2 and sum of yi minus mu, and if we differentiate inside, the minus goes out, this one becomes plus. Okay, and this is the first differentiate of the mu, and let's put it 0, and let's solve this one with respect to mu, and then this one is sum of yi minus n mu equals 0. So this one becomes mu hat is sum of yi divided by n, which is y bar. And actually to maximize this one, there's one more constraint. Here this function, actually we can write this part different way. This part is sum of yi minus 2 yi square, sum of yi square 2 sum of yi mu plus mu square. Okay, and this one can be rewritten as n mu square. This one can be rewritten as n times mu minus, if we get this n out, then n over come inside, and so y bar squared plus constant c. So this thing can be expressed this way, and since we have minus sign, the shape, so this part is mu, and the shape of the log L mu would become like this way, and the maximum value can be achieved from mu equals y bar. Okay, and so this function, this this function depends on mu, and mu is only residing here. And if we re-express this this part this way, then this can be rewritten as this one, and so the shape of this becomes like this, and the maximum achieved at when y bar is here. And actually we have restriction that mu is greater than mu 0. So if mu 0 is here, so if mu 0 is less than y bar, so if mu 0 is less than y bar, then our mu hat is y bar. If mu 0 is greater than y bar, what if mu 0 is here? If mu 0 is greater than y bar, the maximum should be achieved from mu 0. So the MLE in this case is mu 0. MLE in this case mu 0. So our MLE can be written this way. If mu 0 is less than y bar, then MLE is y bar, and if mu 0 is greater than y bar, it is mu 0. So this is mu hat, and our sigma square hat is here, and we have mu hat here. And now let's put our mu hat and sigma hat inside of here. So our L omega hat would be 2 pi minus n over 2 sigma 0 square hat minus n over 2, and e to the minus 1 over 2 sigma square hat times this. For this part, it is sum of yi minus mu hat squared, and actually 1 over n times n, this one is sigma 0 square hat, and so this one and this one can be cancelled out, and so this part can be rewritten as e to the minus n over 2. Okay, now we have L omega hat is here, and we have L omega 0 hat here, and so we can calculate the lambda. Lambda is L omega 0 hat divided by L omega hat, and this value becomes let's see, omega square divided by omega 0 square n over 2. Okay. And I will move on the proof from the next slide. So from the previous slide, we calculated lambda this way, and the lambda is can be expressed in two different ways under these conditions. So if mu 0 is greater than y bar, then mu hat is mu 0, and and that is the sigma 0 hat. Sigma 0 hat is here mu 0 hat is mu 0 under the null hypothesis case. So in this case, the upper part and lower part is the same. So in this case, we have 1 for our lambda, and if mu 0 is less than y bar, then this value would be sum of yi minus y bar square divided by sum of yi minus mu 0 squared. Okay, so we will have something like this, and this integration is of course from I equals 1 to n, I equals 1 to n. Okay, and from here actually the rejection region can be selected from lambda is less than k. This would be our rejection region, and 1 is the maximum value that we can achieve. So we don't need to consider this case. This is the maximum case of the lambda. So we will only focus on this case. And to do that, let's check how we can re-express this one. So sum of I equals 1 to n yi minus mu 0 squared. This one can be written as I equals 1 to n yi minus y bar plus y bar minus mu 0 squared. And this one can be rewritten as sum of I equals 1 to n yi minus y bar squared and plus sum of I equals 1 to n 2 times yi minus y bar times y bar minus mu 0, and plus sum of I equals 1 to n y bar minus mu 0 squared. And actually this part is 0, so this part goes away, and so for this expression we can rewrite it this way. So this part is sum of yi minus y bar square, and this part can be sum of yi minus y bar square plus actually here this is all constant, and so summing I equals 1 to n, actually this is n, so this is n times y bar minus mu 0 squared. Okay, and this expression can be rewritten as this way. We divide this quantity to both the numerator and denominator, and this one becomes n y bar minus mu 0 divided by sum of yi minus y bar squared. And rejection region is this thing is less than k. Oh, actually I missed something. I missed here from lambda, from here this one to the n over 2. I missed this quantity. However, this is okay. What we want is lambda is less than k, and if we move this one to the other side, this one becomes 2k to 2 over k. So we can set up this one as k prime, and so this part, removing this part is okay. Okay, and from this expression, we can rewrite 1 over k minus 1 is less than this thing, and y bar minus mu 0 divided by sum of yi minus y bar squared. Okay, and we can set up this one as the other k. So let's k to the 2 over n is k dash. So this is k dash, and 1 over k dash minus 1 is the other k2 dash. And this is our rejection region. And let's think about this situation. The t statistic is square root of n y bar minus mu 0 divided by s. This is our t statistic, and here s squared is 1 over n minus 1 sum of yi minus y bar squared. And so if you check this one, actually you can rewrite that t squared is greater than another k third. And so this is your rejection region, and so your rejection region becomes t is greater than k, square root of k. So k maybe k fourth or something. So you can derive the rejection region can be written as k is greater than t. K is greater than t. You can rewrite your rejection region can be written this way. Okay, and so yes, actually that's it. Since you know the t distribution, you can calculate the value k from the t distribution. The alpha level, you can calculate the something like probability of t is greater than k under h0. This is alpha, and so you can calculate k, and you can do the test, the likelihood ratio test. And actually deriving this rejection region is equivalent to the one that we calculated from section 10.8. If you go to the section 10.8, you derived this t statistic. You derived the rejection region of this one, the same thing, from section 10.8. So likelihood ratio test and the results from the section 10.8 are equivalent. And actually, all the results from section 10.8 and 10.9 can be obtained by this kind of likelihood ratio test. So if you want to practice more, you can do more exercise, something like these. Then you can find out that the one that you learned from section 10.8 and 10.9 can be also obtained like using likelihood ratio test, just like this way. Okay, so far we learned the log likelihood ratio test. which is the rejection region, can be decided by lambda is less than k. And this is the result from likelihood ratio test. And there is one more, one very useful theorem, the approximated distribution of lambda when n is large. So there's a very useful theorem. Let y1 to yn have joint likelihood function of this, and let R0 denote the number of free parameters that are specified by the null hypothesis, and let R denote the number of free parameters specified by the whole space. Theta is inside of omega. Then for large n, when n is large, minus 2 times ln lambda has approximately a chi-square distribution with R0 minus R degrees of freedom. So this is very useful theorem when n is large. Previously, we derived distribution from the definition of this thing. However, this is kind of tricky. But if we have enough number of n, we can just calculate minus 2 ln lambda, and this one follows chi-square distribution with R degrees of freedom R0 minus R. So we can construct the rejection region based on this result. So this is a lot more convenient than deriving everything just like previous example. And for the proof of this theorem, this is beyond the scope of the course, so I will skip it. But we will going to use this theorem when we are solving the example exercise problems. Okay. Let's move on to example 10.25. Suppose that an engineer wishes to compare the number of complaints per week filled by union stewards for 2 different shifts at a manufacturing plant. 100 independent observations on the number of complaints gave means of x bar equals 20 for shift 1 and y bar equals 22 for shift 2. Assume that the number of complaints per week on the ith shift has a Poisson distribution with mean theta I for I equals 1 and 2. Use the likelihood ratio method to test the null hypothesis is theta 1 is equal to theta 2 versus alternative hypothesis is theta 1 is not equal to theta 2 with alpha is approximately 0.01. And so the x samples are from shift 1, and shift 1 follows Poisson distribution with mean theta 1. So x1 to x, and we have 100 samples, 100 independent samples. They are following Poisson theta 1, and we have y1 to y100. They are also from Poisson theta 2, and the density function, the distribution function is f theta x is 1 over x factorial e to the x theta minus e to the theta. Wait, actually this is theta to x and e to the minus theta. Okay, so this is the distribution function for the Poisson case, and here we want to do the test of this using likelihood ratio test and we have large number of samples. So what we want is we want to calculate lambda, which is L omega 0 hat divided by L omega hat, and we want to use the result that minus 2 and lambda follows chi-square distribution with these degrees of freedom R0 minus R. Here R0 R0 is 2. We have two parameters. R minus R0. Anyway, in the space, in the omega space, it is theta 1, theta 2. Theta 1, theta 2. For both theta 1 is greater than 0, theta 2 is greater than 0. And what about omega 0? Omega 0 is theta 1, theta 2, where theta 1 is equal to theta 2. And both are greater than 0. Okay, and so in the space of omega 0, the dimension is 1, and for the space of the omega, the dimension is 2. So 2 minus 1 is 1. So chi-square 1 minus 2 ln lambda will follow chi-square 1 distribution. And so the thing that we need to calculate is just calculating L at these two. So what is the likelihood function? L of theta 1 and theta 2. The likelihood function is that 1 over product of I equals 1 to 100 xi, product of I equals 1 to 100 yi, and theta 1 to sum of xi, theta 2 to sum of yi, and e to the minus n theta 1 and e to the minus n theta 2. Okay, so this is likelihood function, and under omega 0, theta 1 is equal to theta 2. So let's say this is theta. Then under omega 0, L theta is, let's say this is constant k. So L theta is k times theta to sum of xi plus sum of yi, and e to the minus 2n theta. And let's calculate the maximum likelihood under this situation. So let's take log of the ln L theta. This is ln k plus sum of xi plus sum of yi, ln theta minus 2n theta. And if you differentiate with respect to theta, this one becomes sum of xi plus sum of yi divided by theta minus 2n. And let's put it 0, and then you can calculate theta hat. Our theta hat is sum of xi plus sum of yi divided by 2n. And if you differentiate it again, you can check that sigma. If you differentiate ln L theta again, and put theta hat here, then you can check that this one is less than 0, and so this is the maximum likelihood under the omega 0 space. And also I will leave it to you. Actually you can under the other space, the theta 1 hat is sum of xi divided by n, and sum of theta 2 hat is sum of yi over n, which is x bar and y bar. And so so you can calculate it by yourself. Actually this is very similar to here. And if you calculate these values, and then you can move on to calculate this thing, it is just put these maximum likelihood estimates to the likelihood function, and so then the lambda can become this way. Lambda can become k times theta hat to the theta 0 hat to the sum of xi plus sum of yi, and e to the minus 2n theta 0 hat divided by k times theta 1 hat sum of xi e to the minus n theta 1 hat, and theta 2 hat sigma yi e to the minus n theta 2 hat. Okay, so your lambda is this thing. And I'd like to fill everything inside this slide, but probably the space is not enough. So I will explain from here, from the next slide. Okay, so from here, from lambda here, k can be cancelled, and here theta 0 hat is 2 over x bar plus y bar, and theta 1 hat is x bar, theta 2 hat is y bar. Okay, and so if we put these, you can find out that this thing also cancelled out, and so what's left is lambda is and x bar is 20 and y bar is 22, so theta 0 hat is 21, and so this one is 21 to 100 times 20 plus 22, and over 20 to 100 times 20, and 22 to 100 times 22. This is lambda value, and actually what we want is we want to calculate minus 2 ln lambda, and so this is minus 2 times ln lambda is 100 times 20 plus 22 ln 21 minus 100 times 20 ln 20 minus 100 times 22 ln 22. Okay, and so you can use your calculator to calculate this one, which is 9.527, and we can calculate and this is this value follows chi-square 1. So So you can calculate level 0.01, the threshold, using R. So this is how you can calculate the threshold value, 6.63, and 9.527 is greater than 6.634. So we will going to reject the null hypothesis. Reject H0. So this is our result, and also you can calculate p-value using this value directly, 9.527. If you put it like this way, you can calculate p-value. Okay. Let's move on to exercise problem 10.106. A survey of voter sentiment was conducted in 4 mid-city political wards to compare the fraction of voters favoring candidate A. Random sample of 200 voters were polled in each of the 4 wards, with the result as shown in the accompanying table. The number of voters favoring A in the 4 samples can be regarded as 4 independent binomial random variables. Okay, so this one, this is x1. Let's say this is x2, and this is x4. Then they are from 4 independent binomial random samples. So x1 follows binomial with n equals 200, and the parameter is p1. Yeah, so something like this. And construct likelihood ratio test of the hypothesis that the fraction of voters favoring candidate A are the same in all 4 wards. So the H null is all 4 fractions are equivalent. P1 is equal to P2 is equal to P3 is equal to P4. This is H null, and the alternative is not H0. Okay, and we know that x1, x2, binomial 200p, so 2, and so on. And so the likelihood of the P1 to P4 is since the binomial density is 200, choose x, P1 to x, 1 minus P1 to 200 minus x. So the likelihood of the combined likelihood is product of is 1 to 4 and 200 to xi, and pi to xi, and 1 minus pi to 200 minus xi. Okay, so this is the likelihood function, and and this is binomial likelihood case, and the next thing is calculate MLE. Calculate MLE for theta zero space, and in this space P1 to P4 are all equivalent as P. So where P is equal to 1 equals 1 to 4, 200 choose xi, and p to the xi, 1 minus p to the 200 minus xi, and so let's take log of this thing, and log of LP is log sum of log 200 choose xi, and plus sum of xi log ln p. Let's take ln, and plus 200 minus xi sum of 200 minus xi times ln 1 minus p. Okay, and you can differentiate this one with respect to p. So ln lp with respect to p is equal to sum of xi divided by p minus 1 minus p sum of 200 minus xi, and set this one as 0, and calculate it with respect to p, and then you will going to actually solve it by yourself, and it would be not very difficult to find out that p hat is sum of xi divided by 800, and also under the full case, you can derive the maximum likelihood of P1 hat is x1 over 200, and P2 hat is x2 over 200, derive them by yourself, and I think it would not be very difficult if you specify the right likelihood function and differentiate with respect to p for the omega 0 case, and if for the omega case differentiate with respect to p1, p2, p3, and p4, then you will get maximum likelihood of these, and I will finish the proof from the next slide. Okay, from the previous slide, we want to calculate lambda, which is L omega 0 hat divided by L omega hat, and this is from the likelihood sum product of I equals 1 to 4, 200 xi, and p hat xi 1 minus p hat 2 200 minus xi, and the denominator is integrating product of 1 to 4, 200 choose xi, and here is p1 hat xi 1 minus pi hat 200 minus xi. Okay, and actually this part cancelled, and so this is actually p hat sum of xi and 1 minus p hat sum of 200 minus xi, and divide by product of I equals 1 to 4 p I x I times 1 minus p I hat 200 minus xi. And actually, you can calculate this lambda, but let's we want to calculate minus 2 ln lambda, and so but when we are putting all the numbers here, sometimes we get infimum. So the good strategy is calculate this number. So this is minus 2 times ln sum of xi times ln p hat plus sum of 200 minus xi times ln 1 minus p hat, and minus ln sum of ln pi hat times xi minus sum of ln 1 minus pi hat times 200 minus xi. Okay, so calculate this value, then you will get, so using the calculator you can calculate this equation and you will get 10.54, about 10.54, and here the degrees of the free this one follows chi-square distribution, and the degrees of freedom for the full space is 4. The restricted space is 1, so chi-square distribution with degrees of freedom 3. So with alpha level 0.05, you can calculate the threshold of this, and so 10.54 is greater than 10.54 is greater than 7.81, so we will reject the null hypothesis. Reject H0. And also you can calculate p-value directly using this. And so this is end of the proof. Okay. Here is homework for chapter 10.11. Okay, this is end of the chapter hypothesis testing, and I hope you know you learned a lot about hypothesis testing in mathematical way, and I hope you can apply the knowledge about hypothesis testing from the outside of the university without much of the problem. And okay, thank you. And in next week we will move on to next chapter. That would be a linear model or something like that. Okay, thank you. See you next week.